Thanks, David. Okay, so this presentation is to talk to you about how we can use very conventional data types, so standard seismic and conventional well logging data, to extract the different types of information that we need in order to build up a completely integrated and complete understanding of a more unconventional reservoir such as the Barnett Shale, which is, as we've said, it's a shale gas. So although the first methane gas production in the US was back in the 1820s, the Barnett Shale is a much more recent discovery, although a very established one. It was discovered in 1981, and to date there's been a prolific drilling campaign, some 8,000 plus wells to date. So as we know, the main challenges of a gas shale are the low permeability. In order to be able to realise the hydrocarbon, we need to identify the zones for hydraulic fracture stimulation. But at the same time, the positioning of that is very important. We need to have careful well placement and fracturing relative to the collapsed structures. So all that means that we need to have a very good understanding of our subsurface. So let's think first of all about the hydraulic fracture stimulation. In order to decide what fluids and what propellants we're going to use for the fracking process, we need to have an understanding of the mineralogy and the mechanical rock properties that we're going into. So the brittleness of it is going to affect the fluid type that we use, and the closure stress is going to affect the propellant type. A great source of information for this sort of data is, of course, core data. But core data is very limited. It will be limited very vertically within the wells, and of course it won't be available in all of those wells. So what we're looking for is a way of getting the information that we get from the cores and propagating that out, extracting information from going out to the other wells to try to spread that information. So if we can calibrate the core data and the log data, we can extend our reservoir knowledge. We can use petrophysical modelling to consider the brittleness and the ductility. And we can use petrophysical modelling to look at the kerogen content, the organic content in the shale. And then what I'm going to lead into after that is where we can bring seismic data into this story to get an even greater lateral extent of the information, fill in the gaps between the wells to look at shale thickness and many, many more characteristics that we can get from extracting the seismic information. So what we're trying to do is we're trying to rank the shales within the wells. Obviously we've got the greater vertical extent of the log data beyond the cores, and we've got the lateral extent of that drilling. If we can rank those shales from the well data, we can take that ranking into the seismic and build up a much more comprehensive picture of the zone. Okay, so the first thing we'll look at is brittleness. Brittleness is obviously what we're looking for in terms of how we can do the fracking, and we can do that from the petrophysical modelling. This is a very simple approach. We can look at Poisson's ratio and Young's modulus. If we cross-plot those within the wire-eyed logs, we come up with zones of higher ductility and higher brittleness. Now, of course, this is telling us about brittleness within the reservoir zone, but it's also telling us about ductility, which is also important for the seal. So we need both types in order to have something which is useful to us. So looking at the zones that we've identified from the log data, if we cross-plot just the data from the Barnett Shale, we can see that that falls very conveniently into a very brittle classification. Okay, so that is the Barnett Shale, the brittle Barnett Shale that we're going to be able to frack, and that's where we're hoping the hydrocarbons are going to be. So let's think about the hydrocarbon content, and let's go a little bit further into the petrophysical modelling. Okay, and we're going to concentrate first of all on understanding the mineralogy. Now we're looking for the kerogen content, that's going to give us a lot of information, and that can be mapped directly from the high gamma ray logs. So where we see spikes in the gamma, then that can be related to the kerogen content. So what we're going to use is a paradigm application called multi-min, which is a multi-mineral application, which allows us to build a model of the different minerals within the well. We can put in a proposed model of different minerals and fluids, and we can adjust that model, and then using the principle of optimizing petrophysics, we can get a prediction from the model, generate predicted curves, and what the software is going to do for us is try to minimize the difference between the predicted curves and the measured curves. We can run this iteratively, adjusting the mineral content until we get a good match for the actual logs that we've measured in the wells. So what we start with is we start off with some standard minerals, and we've put in a special mineral which equates approximately to coal, but we've got an elevated gamma ray. So this is what we're saying is representative of our Barnett Shale, and we want to try and model that to see how that looks with the logs that we've measured. So this is the first analysis, and we can see the kerogen volume that we've got. It also calculates for us the gas field porosity, which is obviously ultimately what we're interested in as well. And we've got the various other minerals that we've put into the model. And what we're trying to do is understand how good that first analysis is. How close are we with the mineralogy that we've predicted? Well, what the software gives us is some quality control curves so that we can see how well we're matching on the model versus the data. And we've got mismatches in some areas on the density and in some areas on the TMPH. Now, what we now need to do is adjust things slightly, try and come up with a better model for the kerogen so that we can get a closer model. You can see that the kerogen is spiking very dramatically in the areas where we've got gamma ray peaks. It's directly correlated to that. So we need to try and come up with something which is a little bit more stable in the prediction of the kerogen content. Now we can use the PASSI method to come up with a different methodology for calculating kerogen content. Now this states that if you overlay the resistivity and the sonic on a log scale, then the separation of these curves is a representation of the total organic content. So what we need to define is a baseline interval, so we need to define a baseline away from the reservoir, and then we can use this calculation directly to give us a better estimation of the kerogen. Now we can do this calculation within the loglan application, so this is a mathematical operator using the logs, and using that we calculate a kerogen content, and then we can put that into the multi-min calculation. So we're refining our model by coming up with a different way of considering that first guess of the kerogen content. We can modify the PASSI approach, modelling a sonic curve using the resistivity transform, and that gives us another calculation of the kerogen. So if we put that into the multi-min calculation and look again at the results, then we're getting closer. We're modifying the kerogen, so we're not getting the significant peaks directly related to the gamma ray. So looking at the different curves here, the red curve is the new kerogen, the green was the original, and the modified PASSI is the blue. So using the modified PASSI for the kerogen, we've come up with something a little bit more equalised in terms of the kerogen content. So looking again here, you can see that we've got rid of those massive, significant peaks directly where the gamma ray peaks are. But we can take that one stage further by adding a second special mineral. So we're fairly happy with the kerogen content, but we know that there's something else still affecting the mineralogy in the well. So we modify the first special mineral so that now looks pretty similar to kerogen itself, and we've put in a second special mineral which relates very closely to pyrite. We run the multi-min analysis again, and we can look at the new model. And now we've got something much more reasonable. Looking again at the different coloured curves on the right, we can see the multi-min kerogen with the gamma ray using the special mineral too. The central curve has lost those significant peaks. Oh. So finally, just going across that workflow, the first attempt in the red was simply calculating the kerogen directly from the gamma ray. Then in the centre we used the modified PASSI kerogen, and then on the right we've added in the special mineral, the pyrite, so the kerogen itself now is looking much more robust. So this has given us a pretty good analysis of the kerogen content, the variation of the kerogen within the well, within the zones where we have the logging. And as you know, we have a large number of wells in the Barnett Shale, 8,000 plus points drilled. So a traditional approach may be to just simply extrapolate all of those points across the 8,000 points, but that can't give us a full and complete picture. What we really want to be able to do is relate that directly to the seismic data and then make use of the additional information in the seismic to pull out more information. So we'll do that. We've now overlain the well data directly on the seismic. So as you know, we've ranked the shales from the well data and we know exactly the zone that we're interested in, and we now need to see where that exists within the seismic. So now we come into seismic interpretation and where we can extract further information. We start off with something pretty standard. We need to do a horizon interpretation. And now the Barnett Shale itself is not particularly interpretable. It doesn't come out as a huge booming event on the seismic, but we have the Marble Falls above and the Ellenberger below. So they're nice events that we can use to delineate the zone that's going to be our zone of interest. Now we use a waveform propagation, 3D propagator, to automatically interpret across those two good strong horizons, and I'll show you an image of that propagation and what that propagation itself can tell us in terms of additional information. But first of all, let's consider the Barnett Shale itself. What we also need to think about is the fact that the Barnett Shale is within that zone, but it's not the complete zone. And there's a lot of information between the Marble Falls and the Ellenberger, and we need to zone in and work out exactly where we need to be considering. So, looking at the interpretations that we've done directly, we've got the propagation, the propagated event, which is that image on the top left, and we've just coloured that by dip. Now, because we've done a completely automatic 3D propagation of the event, there's a huge amount of information being brought out to us simply because it's an automatic process, and we can colour that and see the structure. The second image is an eigen attribute from the coherence cube technology, and this can give us an idea of the major faulting zones. Now, as you know, we need to be concerned about natural fracturing in these shales, but also the major fault zones and the karst structures as well. So the surrounding structure within this seismic is as important as the location of the hydrocarbon. So we're trying to avoid the major faulted zones, and we can see those karst structures as well. So that's all being brought out completely automatically. We've just done a propagation and then coloured and generated some attributes. So we've circled an area which is potentially an area of interest. It's away from major structural zones. But of course, this is just the structure, and now we need to go back to getting that information about the shale itself. So remember I said the Barnett is located between the Marble Falls and the Ellenberger. What we're going to do is we're going to use isoproportional slicing because we know the Barnett Shale is conformable with those two layers. And we're going to make a large number of slices between those, again, completely automatically, and then start to define zones which are more of the scale of a wavelet so that we can start looking in more detail and try to find the facies that we're interested in. So once we've defined smaller zones within the main unit, we run our trace shape classification. And this is going to be a supervised classification. So what we do is we use a neural network classification to identify how the wavelet shape is changing within that zone. And as the wavelet shape changes, that represents changes in facies. So once we've done the neural network training of the data set, and we then look for a specific set of trace shapes across the entire zone, then we can start to see a classification coming out. So you can see that circled zone of interest on our facies map is looking like we have a collection which could be of representative facies. Something looks quite cohesive in that area. And remember, this is supervised as well because we know what the seismic looks like directly at the well in the zone where we've identified the shales, where we've ranked them. We know what we're looking for at one point, and we're now using the facies classification using a neural network technology to extrapolate that out intelligently to find a zone of interest. But that was looking at just a map. We did some isoproportional slicing and we looked map by map to see if we could see a facies. We can extend that into a volume classification as well, where we can generate attributes from the seismic, and then we can do hierarchical classification to generate a Fasces cube. We can input a number of different seismic attributes and using principal component analysis to identify the major axes of variation within those seismic volumes, we can identify a Fasces cube, and within that Fasces cube, we can then look for three-dimensional Fasces zones of interest. Then we can isolate them, again, automatically using subvolume detection. So within a volume, if you find a voxel within the zone that you're interested in, then the software will automatically identify the connectivity between that voxel and all other voxels to identify the 3D body which represents your zone of interest. We can then wrap that 3D body with an interpretation, and that comes into all of the other information that we have already. So we have our structural maps, we have our Fasces maps, we've now got a 3D body of a potential shale zone of interest. Let's build further on that, still extracting more information from the seismic. So by mixing attributes visually, we can start to see more of the structure coming out at us. So we can automatically detect the karst collapse structures. And in the same way as we could wrap our sweet spot from the Fasces cube, we can wrap those karst structures with interpretation. So we're building a three-dimensional complexity into the interpretation, which will give us the structural setting for the shale that we're exploring. Automatic fault extraction gives us an additional volume, the eigen volume, which again enhances these collapse structures. So we're using different ways of extracting information from the seismic and then using automated interpretation techniques to extract those so that we can put them into our geological model. So let's consider again the seismic. Now traditionally, I've already spent a little bit of time looking at what we can directly extract from the seismic, but traditionally in gas shale environments, the methodology is often just to drill. You get a lot of information, you get a lot of wells, and how much more can we really get from the seismic? Well, looking at the Barnett Shale seismic, it is a completely standard seismic volume, a seismic acquisition. It's onshore acquisition, of course. It's 30-fold, so nothing special. But it is, because it's land acquisition, it's rich azimuth. So let's think about azimuth. Is that something that we perhaps don't spend enough time considering? Is there more information to be gained from this that could be directly related to the gas shale? Well, let's think about seismic decomposition. When we have seismic data, we spend a lot of time working out the best way of decomposing it into different formats which will tell us different things. For example, pre-stack data, that's becoming increasingly important in the interpretation world. People are starting to realise the value of looking at their gather data over just the stack data. In the same way, increasingly we're starting to think more about subsurface domains than acquisition domain. So rather than looking at representing a trace by its offset, we look at representing it by its angle in terms of the subsurface. And we're just beginning to think about whether azimuth can actually give us something extra. So can we recover in situ and continuous azimuthal data from recorded seismic data? And does it tell us anything more about the Barnett Shale? Well, there is already, of course, in the industry, methodologies available. People are starting to work more and more with wide azimuth acquisition. And traditionally, the way of dealing with that is by sectoring the data. So you take your acquisition and you divide it up according to your acquired azimuths. You might, for convenience, divide it up into 6 or 8 sectors. That means you reprocess the data. You have 6 or 8 times that you have to run all of the data through all of the different processing flows. So the number of sectors that you divide the data in is generally driven by convenience. The resolution of those sectors is, of course, compromised because you've had to make decisions, you've had to divide the data into blocks of 6 or 8 azimuth blocks. And as I've said, the effort involved is quite onerous because you have to process the data 6 or 8 times. the integrity of those sectors is not preserved. Now, what do I mean by that? Well, if you take your data and sector it according to your surface acquisition, then the azimuth that you are considering is the azimuth of the surface. But if you consider the ray paths travelling from the structure up to the surface, then that is not the same azimuth. So how meaningful is it to be using surface azimuth? Can we do something different? Yes, we can. We can consider the full azimuth decomposition of the data. What we do is we work in the local angle domain and we shoot rays from the subsurface up to the surface. We're illuminating, and once we've shot this very large number of rays up to the surface, we then map the arrival rays onto the surface acquisition. So rather than taking what you have at the surface and just making the best of it down at the subsurface, we shoot rays from the subsurface, we collect all of the information as we travel through the subsurface, and then we map that to the surface seismic. We're illuminating from the depth. What does this give us? Well, it gives us two completely new types of data, effectively. Reflection data and directional data. Now, the reflection data is defined as the opening angles between a ray pair and the azimuthal variation of that ray pair up to the surface. The directional data is the azimuthal, the dip of the normal to that ray pair, and the surface, closer to the surface, azimuthal variation up to the surface. So two ray pairs, two different ways of decomposing the data, and two very different types of data produced. We generate full azimuth angle gathers in depth. So if we take a single CRP point, you're familiar with a standard representation of a CMP, whether it be an offset gather or an angle gather. Now we're looking at something which is a full azimuth, 360-degree gather. So if we can just run the first movie, please. This is a reflection gather. This is a single CRP point of a reflection angle. And there it goes. So one plane of that data would be a more traditional angle gather representation. In sectoring, you may have 8 of those, but we have the full 360. And then, of course, using our visualization tools, we can put opacity into that and really start to understand azimuthal variation. So you saw, as we went round that cylinder of data, the way the data was dipping up and down, that's directly the anisotropic effect. Anisotropy is important to us in the Barnett Shale because that is affected by the fracturing, the stress directions. Okay? So how much more information can we get if we've really got that full 360 view? We're not having to say, well, it's approximately 30 or it's approximately 60. That's roughly what my stress direction is. We can look at the full 360 and then decide exactly where our axes are. If we take a look at the second movie, then this is directional data, and this is a completely new type of data. This is representing it's more of an interpretation tool, because at each depth point going up that gather, the unit sphere is mapped onto a disk, and the maximum specular energy arriving from the ray points at depth gives you that bullseye. So that bullseye tells you the angle and azimuth of the subsurface dipping event. It's a direct interpretable information. Okay? Now, by filtering data according to these different types of data, we can use the specular energy to really focus on getting the maximum structural image. We can use the reflection data to give us the maximum, more traditional amplitude, angle, and anisotropy information. So, as I've mentioned, looking at the anisotropy around that 360-degree gather is telling us directly, directly the maximum stress or fracture direction in the Barnett Shale. And this, of course, we need to know this for the drilling direction. If we look at another representation of that, then you can see the saddle image of the dip and the peak going around the 360-degree gather, which gives us directly that information. And look at the different ways that we can represent the data. We can use opacity to really understand the internal structure of each CRP gather. We can decompose the data out. Rather than visualizing the data as a cylinder of seismic data, we can look at radiating cylinders out with increasing angle. Or we can take the slices round and look at them as more traditional gathers. So what we're trying to do here is we're trying to give you the full information that you can extract from the seismic and allow you to make the decisions in terms of what you get from that, rather than making that decision before you even start processing and then giving you a subset of what originally existed. Then we have some automated processes which can start to give us some maps and some information which we can directly relate to the Barnett Shale. So we can automatically calculate residual move out. So in a traditional geophysical package, you may pick move out on a standard gather. We do exactly that, but on the full 360. So we're getting more information. It's a full azimuth analysis. And we can run a residual move out inversion. And we can also look at it in terms of amplitude. So if we do an AVAZ, again, a full azimuth AVAZ inversion, then we can get the axis of symmetry, the anisotropic gradient. So fracture density coming directly from the anisotropy in the residual move out, so the kinematic analysis of the seismic, or the amplitude-based analysis of the seismic, two completely independent inversions of the seismic data set. Two completely different maps, therefore, not different maps, but independent maps, which we can then relate. So we've derived a map of anisotropic strength directly related to the fracturing and the stress directions, and the fracture density. How can we relate those? Well, if we cross-plot those, and then look for the significant values of both anisotropic gradient and fracture density, then those fall onto the cross-plot in the red and the yellow zones. We can map that cross-plot space directly back onto the 3D, and now we're looking at the Barnett Shale. We're looking at, underneath it, we've got the structural information, so we can see the major zones of activity in terms of structure that we want to avoid, and we've mapped directly onto that the anisotropic gradient and fracture density. So we're starting to build this integrated picture, bringing all of this additional information into our integrated zone. Another thing we noticed with the Barnett Shale, just by cross-plotting and analysing different data types and what we could get from it, we inverted the data. We ran inversion so that we had P and S impedance volumes. So we can directly relate those to P and S logs from the wells. Again, another way of extrapolating the well data out into the seismic. And then when we cross-plotted the impedances, we found a relationship between the thickness of the Barnett Shale and the impedance. So now we can start to map the thickness directly from these impedance values. So that's another piece of information that we put into the integrated picture. Now we've got the axis of symmetry derived from those inversions that we ran. We map that directly onto the thickness map. So we've got a potential sweet spot, that zone that we highlighted earlier on in the presentation when we looked to find a quiet zone away from the major structural activity. And we've defined our optimum borehole orientation from the full azimuth seismic decomposition. So all of this additional information that we've managed to get from completely conventional seismic data. One too many. Yeah. So just to recap on the workflow. We looked for the brittleness and ductility information in the wireline logs, and we looked at the kerogen content. We correlated the seismic and the shale zone. We looked at the seismic facies and the well, and we did a supervised classification to extrapolate that information out into the seismic. We isolated a sweet spot by considering the karst and the other structurally active zones. We defined our optimum borehole orientation using that additional information that we got from the seismic decomposition. And we've identified the zone for hydraulic fracture stimulation using the characteristics that we've defined. And just a couple of words, another piece of information that of course we need to consider is with fracture monitoring, as has already been discussed, There's a huge awareness in terms of the environmental concerns. So if we are doing fracking, then alongside that, we need to be concerned about the effects of the fracking, making sure that there is a minimum impermeable layer between the fracking zones and drinking water zones. So alongside all of that, a very useful way of making sure that this is all safe is to monitor the microseismic data. And of course, we can bring that into the same integrated visualization environment. So once we've defined the sweet spot, the optimum borehole location, all of those additional pieces of information, bringing the microseismic into the visualization can ensure that we completely understand the environment. So just to summarize, I've tripped you through a number of different technologies this morning. We've looked at a number of different paradigm technologies, obviously. And just to recap on the names of those, we looked at the petrophysical application, paradigm geolog. We did the seismic interpretation using our SeisEarth application. We went into Fasci's classification using Stratomagic. All of the visualization was done within Voxel Geo. Earth Study 360 is for our seismic decomposition, the full azimuth workflow. And ultimately, although I didn't have time to show you that today, we would do well planning and structural modelling in our SKUA application. So efficient, unrestricted workflows, maximising data sharing. So bringing all of that data together, co-visualising all of the different data types, makes sure you do have a complete understanding of your unconventional reservoir. Thank you.
Thanks, Sandra. Well done. Time for a couple of questions. Anybody got anything to ask? I must say it's pretty stunning use of seismic. Yeah, Oz.
Hi, Oswald Clint, Sanford Bernstein. I'm just curious about the appetite for this, what looks like the utmost efficient way to develop a shale gas. And US independents typically very aggressive in wanting to meet growth targets and just drilling for the sake of drilling. So what's the appetite across that universe of companies for this highly detailed approach?
There is growing appetite. We have the Earth Study 360, the seismic decomposition, is the newest of our technologies, and we are still introducing it to the market. But the uptake has at this point been initially in the US, and we are about to start investigations in Poland more locally as well. So there's definite interest in that, the ability to use all of this automation and to do things as efficiently as possible to get the maximum information.
Okay, anybody else? Yeah,
yeah, thanks for a stunning presentation. Did I hear you correctly about illuminating the structures from below? How would you actually do that in principle, in practice?
Okay, well, it's just a different approach. It's effectively a common angle migration. It's a different approach to standard migration. With a standard migration, you take the source and receiver locations on the surface, and you just shoot rows from those locations down. And the disadvantage of that is that, depending on the structure below, many of those rays are going to be wasted. So you get very low illumination through complex structures. The local angle domain migration, instead of that, shoots rays. Basically, from the depth point, we take a constant array of angles, all angles and all azimuths, and we shoot those rays up to the surface, and absolutely everything which is captured, wherever it is, with respect to the surface acquisition, is then mapped to the surface acquisition. So you preserve the maximum information by doing it that way around.
It's a piece of modelling and not a piece of reality. Yeah. Okay. Okay, Sandra, thanks very much. You need to give Oz, who asked you